Welcome. I'd like to welcome you to the first module of the ESCSI series on internal curing. And this module is going to deal with an overview of how internal curing can be used to improve the performance of concrete. Specifically, we have several objectives in this first module. First, we want to understand the difference between conventional or external curing and internal curing. Second, we want to understand a little bit more about why internal curing may be specifically appropriate to be using in modern concretes. Third, we want to understand the science that makes internal curing possible. Fourth, we want to really talk about the properties of concrete that can be improved with internal curing and what we should be looking for. And finally, I want to talk about some recent steps that the industry has been taking to implement internal curing, because this really is an industry-ready technology. Now, just to provide a little bit of background, as we all know, concrete is a widely used material, but there are several infrastructure problems that keep popping their head up. As we can see here, there's a list of statistics where Americans spend a lot of time in traffic jams and reconstruction. A large number of our bridges are structurally deficient, functionally obsolete, and are needing repair. A large portion of our highways are in poor or mediocre condition. And a lot of this comes from the fact that a lot of the concrete is cracked, a lot of the concrete is spalled, and that cracking and spalling really leads to a more rapid corrosion of the reinforcing steel. So what we're going to talk about here is the fact that internal curing can provide one potential solution as we rebuild a lot of this infrastructure to protect our concrete and to make it more likely to last longer. We can make it more resistant to cracking and more resistant to corrosion. So one of the things that we really want to keep in mind is curing is important, and we all know that curing is valuable for our concrete structures. When our concrete structures are placed, they're very sensitive at early ages to how they're cured, to the temperature, to the moisture, and they can be easily damaged if they're not treated properly. We know that it's good practice to try to maintain appropriate temperature and moisture for the first several weeks, and many times we see specifications where they tell us to moisture our concrete for a week or for 2 weeks. Proper curing is important because it's going to enable concrete to hydrate. It's essentially going to allow the reaction to occur between water and cement, and that reaction that occurs is important because it's going to allow the concrete to develop strength. It's going to allow the concrete to become more durable, and by reacting the cement with the water, we're going to fill in the porosity of the overall system. In addition, curing is important because it's going to help us to reduce any stresses that develop if our concrete starts to dry and it wants to shrink and crack. So proper curing is going to be helpful while our concrete is very young to reduce the potential for cracking due to moisture or temperature changes. Now, while we all know that curing is very important, unfortunately in practice we frequently see curing being overlooked as one of the vital steps to ensuring our concrete will have a long service life. Now, when we talk about curing, up till now we've really talked about the idea of conventional curing, or what we'll talk about with external curing. And this really works by doing something to the outside of the concrete after the concrete's been placed. So after our concrete sets, we may do something like placing water on top of the surface, and that water will be a curing water, ponded water on top of the concrete, and that water will actually be absorbed after the time of setting to facilitate further hydration of our cement and to reduce the shrinkage that could be taking place. This is providing extra water to the system and is going to really help to provide the most that we can get out of our concrete. Secondly, another form of curing is commonly used, and this curing may be the value of using a curing compound. And the idea of a curing compound is really to prevent the evaporation of water from the surface. So here what we're seeing is a layer, a film will be formed across the surface, and that film is really to prevent or minimize the water that could be lost due to evaporation. Again, it's a little bit different than what we saw in the first case where water was placed on the surface and that water would be absorbed by our concrete, because in the case of a curing compound, we're really just minimizing the loss of water from the system. It's also very important when we think about the idea of water ponding on our system that we recognize as we move to higher and higher strength concretes, our concretes are becoming much more dense, much less permeable, and that really limits the depth at which that water can get to into our concrete surface. And many times that properly cured layer may be limited to the outer inch or two of our concrete, with the core of our concrete not getting sufficient curing water. Now, as we've talked about external curing, we want to talk a little bit about why is there all of a sudden a need to do something that's different, or why can we get advantages of doing something that's a little bit different? So you may be asking yourself, well, external curing has worked for centuries. Why are we doing something new now? And the whole idea here is really, as we move to higher performance concretes, we're able to make less permeable concretes using a lower water to cement ratio system and using more supplementary materials. Now this is really good because it allows us to reduce the porosity of our concrete, and that's vital because that's going to make it harder for things to move through our concrete. And the types of things that we're talking about are ions like a chloride ion or a sulfate ion, and it's going to make it more difficult for those to get into the concrete to react, or more difficult to reach the reinforcing steel and to start the corrosion process. Now, one of the big benefits of using these higher performance concretes is they limit fluid movement inside of the system. And as we just talked about on the previous slide, by limiting fluid movement, this can actually make it harder to get our curing water into our concrete. The second reason why we're starting to see a big increase in discussion of the potential for internal curing is because as we move to using more and more supplementary materials, these materials are going to require a longer curing time because they're less reactive than our conventional cements. This means that we're going to have the need to keep water in that system for a longer time, and instead of ponding the systems instead of 2 weeks to 3 weeks to 4 weeks, maybe we can supply that water in a different way. In addition, a lot of these supplementary materials have more chemical shrinkage than a classic Portland cement, and this is another reason why we would want to supply additional curing water. Now, what is internal curing? Internal curing is really a process where we're going to allow the hydration of the cement to occur that's exactly like what we've just been talking about, but instead of applying the water at the surface of the concrete, what we're really going to do is we are going to supply the water from inside of the concrete itself. So what we're going to do is we're going to place porous inclusions, or little tiny porous bodies inside of the concrete, and they're going to act as a reservoir of water. Now this water is important because it's not going to be part of the mixing water, and it's not going to be part of the water that really helps to describe or define the initial porosity of our concrete matrix. After the system sets, this water will get drawn out of these porous inclusions, will be drawn out of this lightweight aggregate, and will get to more of the cement paste, allowing it to cure and help the hydration process. Now, the real big benefit of using water-filled inclusions is this curing water is now available throughout the cross-section of our concrete and can really be supplied when it's needed and can be supplied across the entire cross-section. So how does internal curing really work? Well, water can be lost in two separate ways when we start to talk about concrete. And the one we're probably more familiar with is the water that's lost due to drying. If we have an open concrete surface, we have some evaporation taking place, water can evaporate and leave our concrete system. However, we also need to be aware that we can get vapor-filled spaces forming inside of concrete because water is being used as a part of the hydration reaction. And when these vapor-filled spaces start to form, we commonly hear them being referred to as self-desiccation. Now, all cements will undergo this chemical shrinkage, this volume reduction, as the cement reacts. However, what's really important to recognize is as we get to a system that has smaller and smaller pores, the impact of this chemical shrinkage can become much larger. So in lower water to cement ratio concretes, in concretes with finer particles like silica fume or more finely ground cement, the impact of these vapor-filled spaces can be much more dramatic, causing much higher shrinkage in those systems. So what we're really doing with our internal curing is we're going to supply enough water to really replace the water or replace the volume of vapor-filled space that's generated during the hydration process, and we're going to fill that vapor-filled space in with water. That's the whole concept of internal curing. So how are we going to do this with internal curing? Well, the first thing we're going to do is we're going to replace a portion of the fine aggregate with a porous lightweight aggregate that's pre-wetted before mixing. So these porous lightweight aggregates are typically going to absorb between 6 and 30% of their weight, and they're going to contain moisture inside of those pores. As the system is mixed, the moisture will stay inside of those pores, and as the concrete is placed, the moisture will be inside of those pores. However, once the concrete starts to set, these vapor-filled spaces can start to develop because of chemical shrinkage, leading to the self-desiccation that we're talking about. However, the lightweight aggregate has water, and that water can be supplied to the matrix. So water will move from the pores in the lightweight aggregate into the matrix as it's needed, and this will reduce the pressure that develops inside of the fluid. This will keep the paste pores filled, and this will reduce the effects of self-desiccation. Now, some of the advantages of this, it's going to allow more of the cement to hydrate. In addition, it's going to reduce the overall shrinkage stress that's developing. So now, where are some of these different internally cured concretes being used, and where are they being applied? The New York State Department of Transportation has used several bridge decks using internal curing. In general, the experience has been very positive. They've seen a reduction in cracking with really no problems being reported by the contractors or suppliers. Here we can see a photo of some of these bridges being placed. We can also see the map that shows some stars of where these internally cured decks have been or are in the process of being cast. In addition to the work in New York, we've seen that large slabs are being built in the Denver area for some water tanks, and what they were able to observe is internal curing gave them less cracking, which they would believe would lead to lower maintenance costs down the road. And the differences between the conventional and internally cured concretes during placement were relatively minimal. And this essentially had them moving from conventional concretes to internally cured concrete so that they could reduce the potential for cracking. Other internal curing applications, here we can see an intermodal railroad facility where substantial amounts of low slump internally cured concretes were placed. Internal curing has the potential to reduce curling, reduce cracking, and these can really extend the life of pavements. We can also see some pictures here where internal curing was used in some continuously reinforced concrete pavements with TxDOT, where they had the ability to reduce cracking and also to reduce the potential for plastic shrinkage cracking when these pavements were being placed on a high evaporation environment. Further, we've seen some internal curing applications in the state of Indiana. Here we see two bridge decks that were being cast at the same time in 2010. These two bridge decks were to compare a conventional bridge deck mixture and an internally cured bridge deck mixture. Both mixtures had similar workability. They both had similar strength. The internally cured had slightly higher strength. The internally cured had slightly lower diffusion coefficients, but really I think one of the telltale signs was the internally cured concrete contained no bridges, while the plain concrete contained 3 cracks in the bridge. So the plain concrete, 3 cracks, the internally cured concrete had no cracking. Now, does this mean that internally cured concretes will never crack? No. However, what we can say is that we're substantially reducing the potential for cracking when we use internal curing. So in summary, what we've really been able to see in this module is that the infrastructure in the U.S. is aging and deteriorating, and we're going to be repairing and replacing a substantial portion of this infrastructure. Internal curing really offers us one approach to extend the service life of concrete, and the idea here is we can really use internal curing with a lot of our high-performance concretes to really get the most out of those concretes because they may be prone to cracking. Internal curing is done by using a lightweight aggregate, and that lightweight aggregate can be used as a reservoir to hide water throughout the cross-section of our concrete, and by hiding this water we're able to release that water at the appropriate time to increase the hydration of the cement, but also to reduce the shrinkage and shrinkage cracking that may be occurring, especially at very early ages. Finally, what we've seen is there are several different groups that have been using internal curing on a full-scale basis. This internal curing is as simple as replacing a portion of the sand in our system with fine lightweight aggregate that's been pre-wetted. These examples have been shown, and in practice this is showing great potential. The one thing we do need to be aware of is we do need to do quality control testing on our lightweight aggregate to make sure that we understand our moisture content. But once we've done that, and once we've done our proper adjustments for our moisture content, this really looks and places like a conventional concrete. So I'd like to thank you for tuning in to the first module here, and I'd like to give you a little bit of insight in what's coming up in some of the upcoming modules that will be part of this series. Internal curing will be described as a way to get more of our cementitious material, and we'll talk how this influences hydration in much greater depth. We'll also give a few modules where we really discuss the ideas on how we proportion these internally cured concretes and come up with the mixture designs that we're going to use. How do we know how much of the sand to replace with lightweight aggregate? We'll also talk in more detail about how internal curing reduces shrinkage and reduces the potential for shrinkage cracking, and we'll show some calculations that can be done to quantify these effects. This is really one of the main aspects of internal curing that's beneficial, and what we're going to see is that this works better as we start to use more supplementary materials. This works better as we go to higher performance concretes. So we really have a solution here that can solve one of the real Achilles heels of these high performance concretes, and that's their crack susceptibility. Finally, what we're going to really focus in on is how internal curing can be used to reduce fluid transport, which will make it more difficult to get the steel inside of our internally cured concretes to start to corrode, because it's going to take longer for the chlorides to get there. And by doing this, we'll be able to increase the sustainability of our concrete. So while we've gone through this first module and we've thank you for paying attention. I also would like to draw your attention to some other information that's out there on internal curing, and you can also find several of these references and additional references located at the ESCSI website. And with that, we'd like to thank you for your attention and hope that you'll be able to tune in for some of our additional modules. Thank you.